psi, and then is going up. Okay. So those are our two values due to the shear. Okay. Then we are going to look at element A again. We're going to determine the shear due to Vx and Vz. Okay. So we're going to focus on element A. So if we look at our direction for Vx, okay, so Vx is in this direction. And then Vz, right? I'm going to check. Yeah. Vz is in that direction. Yep. So it's 600 and 500. So this is 600. And this is 500 pounds. And this is over here. This is our element A, right? So we know for element A, right, the shear over here, the shear due to Vz or Vx is equal to what? 0. We know that, right? Which we have earlier, right? Vx at A, the shear is equal to 0. However, Vz is not equal to 0. Okay. And what I want you to take note, so now the formula now, right? So we just need to just write the shear first at point A, give a bit of space where you see why. So we know that it's equal to Vx over Izz Qz over T plus or minus, okay, or yeah, we plus or minus, or for this case we just put a plus if the direction is opposite. Ixx Qx over T. Okay. So we know that this term is equal to 0. So now if we were to construct the shear flow, right? I want you to pay a lot of attention down here, okay? This is important. So we know that this over here is our XX direction. Okay. So if now I were to construct our shear flow, right? Okay. It's in that direction. Okay. So let's calculate the value first. Okay. Let's calculate the value first. So we know our VZ, so QX is equal to the formula is equal to area, right? So the area is half of the so pi r squared divided by 2, and y bar, and as I said, I will provide the formula for this, is 4r over 3 pi, right? You can see over here, 4r over 3 pi. Okay, so it's equal to 4r over 3 pi. Okay, so this is the area, right? And this is the z bar. Okay, so it's equal to 4r. Let me check again. 4r over 3 pi. 4r over 3 pi. That's correct. So now we can simplify this equation. Cancel the pi. Cancel the pi. Cancel the 2. So this is equal to, I do apologize. Okay, so 2. So this is equal to 203 R cubed, right? So you can consider pi R cubed. So the Qx is equal to R is equal to 1, so it's equal to 203 inches to the power cube. Okay. So now we know that looking at the direction of the shear, right? You know this arrow over here is pointing towards the Y. So shear, the plane is Y and in the Z direction. The shear flow is going in the Z direction. So this will be equal to Vz 600 2/3 over the IZZ and IXX is equal to what? Is equal to, we calculated this. 0.785. And the thickness, okay, so this is the thickness now, is 2 inches. Because the radius is 1, diameter is 2. 600 times by 2 over 3 divided by 0.785 divided by 2. 600 times 2 over 3 divided by 0.785 divided by 2 is equal to 254.77 psi. Okay. So this is for element A. Okay. So I'm going to do on the side element B, right? Same thing, right? So element B, I'll not be more than 5 minutes, okay? Element B, right? So same thing. Now element B is now over here, right? So again, we have our VZ and we have our what? Vx, right? So we know, right? Vz, which is equal to 600 pounds, the shear will be the shear due to Vz is equal to 0, right? So the only thing that we have to care now is the 500. Okay. So now if I were to draw the centroid, right? Now the shear flow will look like this now. So for this case, right, we know the shear, we're calculating shear y, z, no, y, and it's now in the x direction, right? So this is again equal to 500 multiplied by 2 over 3, right? The first moment area is the same, 0.785, and then multiply by 2. Okay, so 500 multiplied by 2 over 3 divided by 0.785 divided by 2 is equal to 212.314. Okay, the last part is where it's the most important. What do I mean by that? I want you to focus on element A, okay? And we are going to highlight element A. I want you all to see the shear direction. So the one on top is the shear due to the torque. The one below is the shear due to the what? Shear force. So you can see both of them are in the what? In the same direction. Okay. The fact that they are in the same direction, right? You now can write shear YZ at point A is equal to 4.586 times 10 to the power 3 plus, because they are the same direction, right? Plus by 254.77, right? So this is equal to 4.586 power 3 plus at 254.77 is equal to 4.841 times 10 to the power 3 psi. Okay, and then the shear YZ, YX at point B now, right? And point B, again, you can see that they are in the what? The shear flow and the torque. I mean, the torque induced on the shear stress and the shear flow are in the same direction, right? Because it's the same direction, you add them. If it's different, you minus them. Okay, so this will be equal to 4.586 times 10 to the power 6 plus 212.314. Okay, so this is equal to 4.586 plus 212.314 is equal to 4.586, not power of 6, which is power 3. 4.586 power 3 plus 212.314 is equal to 4.798 times 10 to the power 3 psi. Okay. It's the shear that is always the confusing one. So just to quickly finish off. So if I were to draw element A, right? So it has a shear is in this direction. So this is equal to 4.841 times 10 to the power 3. And then there's a normal stress in the what? In the y direction for element A is 17.579 in the y direction. Okay, so y direction 17.579 times 10 to the power 3 psi. So this is for element A. Now, if we were to draw element B, right? So element B, the orientation is different. And we have a shear dealing with this direction, right? And the shear is 4.798 times 10 to the power 3 psi. And then we have a compression 5.86. We have a compression 5.86 times 10 to the power 3 psi. Okay. So that's how you handle questions like this. Okay. And that's all I have for today. As I said, there are software to do this, but they're really expensive. Okay. So that's why that's the purpose of teaching you guys doing hand calculation. I'll still stay behind.